Before we start discussing the normal distribution, which is a continuous function, let's take another look at the binomial distribution, which is a discrete function. This binomial distribution is one where n equals 5 and p equals 0.5. What makes this a discrete function is that there are no values between those shown. That is, the probability calculated for x equals 0 is 0.0312, and the probability for x equal 1 is 0.1652. The function has no values between the probability of x equals 0 and the probability of x equals 1. A continuous function, on the other hand, does not have any instantaneous changes in its values. The function shown in black is a continuous function. It happens to be a normal distribution we will discuss momentarily. Notice that there are no instantaneous changes. This is the equation for the normal distribution. Let's briefly discuss each of its terms. Mu is the mean of the distribution. Sigma appears in two places and is the standard deviation of the distribution. Pi is the same constant we've seen since high school. E is the base of the natural logarithm. X is the independent random variable, and y is the dependent variable. The normal distribution shown here has a mean of 0.0 and a standard deviation of 25. If we let x equal minus 50, located here, the resulting value of y is 0.0022, shown here, giving us 1 point on the normal distribution. Because the normal distribution is a continuous function, there is a value for y for every value of x. When x equals minus 25, y is equal to 0.0097. When x equals the value of the mean, y reaches its maximum value. We will discuss further the effect of the mean and standard deviation on the normal distribution in a few moments. The main point here is that for any value of x, there is a calculated value of y. Now that we understand where the normal distribution comes from, the question now is, how does it relate to probability? Just as we did when determining the probability for the histogram, it is the area under the curve that comes into play. More specifically, the area under the curve to the left of the x value. As x increases and moves to the right, the area to the left of the x value increases. As the x value increases further, the total area under the curve increases further and ultimately reaches a value of 1. This fact that the total area under the normal distribution is 1 is true for all values of the mean and standard deviation. We will explore this property momentarily. But first we introduce the cumulative distribution, shown here in red, and is drawn to the scale here to the right. It approaches 0 as x values become much less than the mean, and approaches 1 as the x values become much greater than the mean. It represents the area under the normal distribution as x moves from left to right. This particular distribution has a mean of 0 and a standard deviation of 25. If mu, the mean, becomes less, the distribution shifts to the left. If mu increases in value, the distribution shifts to the right. Notice that the distribution does not change height, nor does the total area vary from 1. The total area under the normal distribution is always 1. As the standard deviation decreases, the maximum value of the distribution increases. As the standard deviation increases, the maximum value of the distribution decreases. Notice that the changes in the standard deviation do not change the value of the mean, or the ultimate value of the cumulative distribution, which is always 1. The cumulative distribution is also a continuous function. For every value of x, there is a value of the cumulative distribution, and this value is the area under the normal distribution to the left of the x value. As x increases and moves to the right, the area to the left of the x value continues to increase. When x is equal to the mean, the area to the left of x is equal to 0.5. As x continues to increase, the area to the left of the x value continues to increase, and the area to the left of x is the value of the cumulative distribution. As x continues to move to the right, the value of the cumulative distribution continues to approach its maximum value, which is 1. It never actually reaches the value of 1, but as x becomes much larger than the mean, the amount of remaining area becomes quite negligible. Let's do an example with a different distribution where the mean is 80 and the standard deviation is 20. We introduce a new variable x with a subscript 1. We refer to it as x1. X is the random variable and can take on any value. We will determine the probability of x being less than x1. Let's let x1 equal 60 and determine the probability of x being less than 60. The probability is equal to the area under the normal distribution curve left of the value of 60. Remember that the random variable x can take on any value from minus infinity to plus infinity. What we will determine is the probability of x being less than 60 by determining the area under the normal distribution curve to the left of the value of 60. The cumulative distribution is the means of determining this probability. For x1 equal to 60, the area to its left is 0.1587, which is the probability of x being less than 60. Let's introduce another variable, x2, and set it equal to 100, and determine the probability of x being less than 100 as we did for 60. This probability is equal to the area under the normal distribution to the left of 100. And the area is equal to the value of the cumulative distribution at x2 equal 100. At x2 equal to 100, the cumulative distribution is equal to 0.8413, which is the probability of x being less than 100. If the probability of x being less than 60 is 0.1587, and the probability of x being less than 100 is 0.8413, it's time to consider the probability of x being greater than x1 and less than x2. Remember that the area to the left of 60 is 0.1587. The area to the left of 100 is 0.8413. It therefore follows that the area under the normal distribution between these two values is the difference in the cumulative distribution for these two values. Therefore, the probability of x, the random variable, falling between the values of 60 and 100 is the difference between 0.8413 and 0.1587, which is 0.6827. In general, the probability of x falling between any two values is equal to the area under the normal distribution between those two values. Therefore, if x2 were to increase, the area between x1 and x2 would increase, resulting in an increase in the probability. Correspondingly, if x1 were to increase in value, the area between x1 and x2 would decrease, making the probability of falling between x1 and x2 smaller. If x2 were to now decrease until it equaled x1, the area between x1 and x2 becomes 0. Therefore, the probability of x falling between two equal values is 0, which is equivalent of saying the probability of x equaling 100 is 0, because there's no area for x equal to 100. There is definitely area to the left of 100, there is area to the right of 100, but there is no area under the normal distribution at 100. We've been talking about the area to the left of the x value, but what about the area to the right of the x value? For the case where x1 equals 100, the probability of x being less than 100 is the area to the left. and equal to the value of the cumulative distribution at x1 equal 100. It therefore follows that the probability of x being greater than 100 is 1 minus 0.8413, which equals 0.1587, and is the difference between 1 and 0.8413. The sum of these two probabilities is therefore 1, and is true for any value of x. The cumulative distribution is the key to finding probabilities. Finding the values of the cumulative distribution will be the subject of the next video.